Modern broadband networks carry voice, video, and multi-gigabit data for thousands of users simultaneously, all flowing as a single, massive stream. Historically, ISPs managed this traffic by drawing a hard line. You had the RF plant delivering physical signals to the home, and the IP routing core handling the traffic logic. Distributed access architecture and Docsis 4.0 shift those logical functions away from the central hub and directly into the access network. DAA pushes digital fiber into the edge network, turning physical access hardware into software problems in data centers. For engineers, traditional silos are gone. You must choose, specialize at the virtualized edge, or scale up to the centralized core. On one side, you have the Docsis edge, which requires hybridizing legacy RF signals with modern cloud nodes. On the other, you have the metro core, where the focus is steering massive volumes of converged IP traffic across regional hubs. Specializing in one of these domains changes your daily technical focus and determines which set of networking protocols you'll spend the next decade mastering. Let's examine the access edge. The modern DOCSS and DAA engineer operates at the intersection of local plant hardware and cloud infrastructure. This architecture breakdown highlights DAA's primary mechanism, separating the logical DOCSS MAC processing from the physical signaling, PHY. Depending on whether the network uses remote PHY or remote MAC PHY, these components are deployed across a digital fiber Ethernet link rather than a single chassis. Because of this split, the engineering requirements shift. You have to manage virtualized, cloud-native cable modem termination systems, or vCMTS. This server schematic shows the result of that transition. The environment has shifted toward generic compute pods and Kubernetes clusters, where network functions run as virtualized modules alongside standard IT workloads. Yet, inside those cloud containers, you still have to parse advanced Docsis 4.0 protocols, configure OFDM channels, and decode TLV MAC management messages. This tier chart demonstrates the payoff for that complexity. By virtualizing the edge, you can deploy a unified access platform, running a virtualized passive optical network alongside legacy Docsis from the exact same compute module. But the cloud-native upgrades do not erase the physical reality of the coaxial cable buried deep in the dirt. HFC plants suffer from dynamic impairments. Temperature changes or water ingress can cause a cable modem's signal-to-noise ratio to drop unexpectedly. When the Docsis standard convolution function fails to adjust for those impairments, engineers still have to manually intervene at the physical layer, fine-tuning elements like the main equalizer tap. To succeed here, you have to straddle two disciplines, managing abstract cloud-native software clusters while actively troubleshooting the physical degradation of RF signals. Moving away from the physical access edge, we enter the IP and MPLS engine of the metro core. This topology map shows the core's structural purpose. High-capacity hub and DSR routers take all that aggregated node traffic and securely route it to regional centers or the broader internet. To operate at this level, the primary requirement is mastering source routing paradigms, specifically segment routing for MPLS. Networks are replacing legacy label distribution protocols with segment routing, which demands a deep theoretical understanding of control planes like ISIS and BGP. Instead of hop-by-hop lookups, segment routing pushes instructions, called segments, directly into the packet header. By embedding the path, you gain absolute control over traffic steering and resiliency. During a link failure, protocols instantly execute a pre-computed backup path, achieving failovers under 50 milliseconds without microloops. The trade-off is isolation. In the core, you operate entirely abstracted from the subscriber's experience and the physical access hardware. At the core, a single routing error can black hole traffic for an entire regional hub, instantly affecting hundreds of thousands of concurrent sessions. This path is heavily protocol-driven and highly theoretical. It requires executing configuration logic with absolute precision across millions of concurrent connections. Choosing between these paths comes down to mapping their technical trade-offs against your long-term priorities. The Docsis and DAA route requires deep specialization in specific access technologies and virtualized edge infrastructure. It fits engineers who want to stay close to the physical plant, integrating hardware with software and solving tangible, real-world signal problems. The metro core requires mastery of global routing blocks, IP MPLS forwarding planes, and massive system scaling. It fits engineers willing to endure a steep learning curve in theoretical networking protocols, in exchange for operating entirely in the abstract. This comparison matrix plots the two options against two critical vectors: industry transferability and niche indispensability. If your priority is broad industry transferability, allowing you to eventually move to tech giants or enterprise data centers, the Metro Core path scores highest. Segment routing and BGP are universal languages across the IT sector. If you prioritize niche indispensability, Docsis and DAA is the choice. Pioneering the convergence of legacy physical plants with modern Kubernetes design is where the most specific innovation inside ISPs is happening right now. As the traditional boundaries between the edge and the core dissolve, aligning your technical skills with one of these paths determines how you'll navigate the next generation of ISP architecture.